Okay, so is the right side
the forward,
forward?
Yeah.
Left side backward. In the middle there's a pointer.
Yeah.
If you want to point something out, the one it's quite small.
Yeah.
It's a big room. Use the mouse. You can
right.
also. And if this is not working on the left side, by clicking on the left side, you can go forward.
Okay, I know. Yeah, very good. That should work.
And there's the microphone. You can change the position of the microphone.
Oh, yeah.
And I don't know the timer. Was someone using the timer?
Well, I've timed it to be a little bit over 40 minutes. So
should I put 40 minutes on it?
Maybe it's a good idea to put it up. So
why not?
40 minutes?
Like 40 minutes, then
should do
So I will put 40 minutes on it?
Yeah, put 40 minutes on.
Yeah,
okay. Very good. Very good.
45. So
I will put 47, start already now.
Okay. Very good. Well, thank you for being here.
Of course.
Yeah. So, well, a lot of interesting meetings, a lot of interesting contacts.
Yeah, good.
And the Pico thing is really working.
It works.
Wonderful session yesterday.
That's the future.
Yeah, I think so too. Very nice.
I will
Thank you
around.
very much. Okay. Yeah, it's really very nice. And it's really an art to trigger imagination with people. Yeah. They say, I've got to see that. That one. Yeah. And people have to get used to that. Some still try to squeeze 10 minutes in 2 minutes.
No. You have to select, much more selective. This is the art, of course.
That's the art.
Because then afterwards you can be a broader on the screen.
Yeah, that's right.
No, but I think it's because it's basically a hybrid between oral and poster. So this is the way to do it.
And then you see the fantastic benefits of having Copernicus here. All this technology, all these people.
Yeah,
it works very smoothly.
Do a wonderful job.
Very impressed. Yeah. But I probably should go down and come up.
Yeah, you can do that way. It looks
a bit more
formal.
No music this time.
No. Welcome. Welcome to this Union Award lecture. In the EDU, we are giving awards at all levels of experience among the scientists. We have awards for the early career scientists, and we have for say senior scientists, and then we have 4 union awards or medals, which are given for lifelong achievements within the sciences. We have one for each of the main columns that is forming the EDU. You can call it the inner Earth, the near surface Earth, and the outer Earth plus planetary sciences. And then we have a 4th union medal, which is also given for outstanding scientific achievements, but which is also reserved for scientists who have performed research in developing regions for the benefit of people and society, through which they have achieved exceptional international standing in the geosciences, planetary and space sciences, defined in their widest senses. So this is the Alexander von Humboldt medal, and the name is well chosen, I believe, because Alexander von Humboldt was the explorer who was a broadly ranging scientist, knowing all the disciplines, and were able to do interdisciplinary research before that expression had even been invented, I believe. And I'm very happy to invite Johan Bouma to the stage to give the award medal. Johan Bouma receives the award for his outstanding contribution to connecting earth science and society using a holistic approach. And you're not here to listen to me, so I will stop with these words and hand over the word to Johan Bouma. And let me just end by congratulating Johan Bouma for his exceptional achievements and also with being the recipient of the Alexander von Humboldt Medal.
Thank you very much, Mr. Vice President. Good afternoon, ladies and gentlemen. It's good to see so many people on Friday. That's a good sign. I like to talk about this man, Alexander von Humboldt. This is him. There is a beautiful biography written by Andrea Wolf, published in 2015, that describes his life, his outlook on life and on science and so on and so forth, and I can highly recommend to you to read that book. Now, Alexander von Humboldt, in the very early part of the 19th century, was the first ecologist, connecting plants and animals with the earth in a web of life, recognizing the importance of geography and climate. In his trips, he also strongly engaged with people and their problems. He was a real scientist, making notes and measurements all the time, with an open and inquisitive mind, practicing inter- and transdisciplinary long before these terms were coined. There's this nice anecdote that he was climbing a mountain in the Andes of 4,000 meters, and he was carrying a little barometer, and he was measuring air pressure every 100 meters while he was going along. He was losing his shoes, and he was walking with bare feet in the snow. That's the spirit, right? In the book, this picture is shown, showing the travel he made. He was in South America. He was in Peru, he was in Mexico, he was in Cuba, he was in the United States. Extensive, certainly in that time. Now, I will try to cover three elements in this presentation here today. First of all, a brief review of soil studies of our group in developing countries and how they relate to Alexander von Humboldt's spirit. Secondly, some aspects of the future outlook for developing countries when considering particularly agroecological developments, and that can only be a very broad brush approach, obviously. And thirdly, and in my view, the most important aspect at this point in time is to explore the leapfrogging potential for soil research in developing countries, considering the widening gap between science and post-truth society in our so-called developed part of the world. First, we go to the Philippines. Work of Marco Wopperijs, Alfred Stein, Henk Weusten. This is flooded rice, millions of hectares all over the world, particularly in Asia. And in those fields, the topsoil is puddled by mechanical action, making an impermeable, very slowly permeable layer so that the water is standing on top. And the rice is planted in that top. Now, one of the problems was there that it was not really known what the hydraulic resistance was of the puddled layer. If it is too high, the water will disappear to the subsoil. And also different techniques produce different layers. So Wopperijs was measuring the hydraulic resistance with a new technique of the puddled layer. This is a measurement in a field. The potential is measured with tensiometers below the puddled layer, so you can calculate the mechanical resistance. He did it on many sites, and he could show that different soil materials produced different puddled layers with different hydraulic resistances, and also that the way the puddling occurred had a significant effect on the hydraulic properties. And that was important because water in many areas is rather scarce, so you want to be sure that your puddled layer is affecting in a right way. He also worked on upland rice. So there, it's a matter of the plant roots of the rice, getting the nutrients and the water from the soil, presenting a rather different situation that he simulated in Tarlac province in the Philippines. You see that here on a map. And used the Oriza model that was already existing, but he could modify it, predicting for different areas the potential or the possible yields that varied a great deal depending on soil type. And this had, of course, obvious effects on the also the planning potential that was associated with this data. One element that he emphasized particularly in the upland rice studies was the effect of water movement in structured soils, clay soils particularly, where water may move quickly along the vertical cracks down and not being available for the plants anymore. It may also collect subsurface in dead-end macropores, we call that internal catchment. And what may also happen is that if you have these large structural elements, the roots cannot penetrate these elements, and the water in there may be available in terms of its potential, but it cannot be reached because the roots cannot suck it out. These elements were brought in the simulation model, and that's why it was much more relevant for the real situation in the field than if you assume the traditional approach where the soil is considered homogeneous and isotropic and swelling and shrinkage does not occur. We move to Vietnam. Acid sulfate soils in Vietnam, Tini van Mensvoort, Le Quang Tri, Le Quang Minh, and Olivier Husson that you see here in the picture. You see here the system that is made there with bunds and with ditches. And what happens here is that you have marine soils that are deposited by the sea, and they contain pyrite. And those soils are wet, and then they are drained. The pyrite oxidizes, forming sulfuric acid and pHs of 2 or 3, and the crops die immediately. Okay, so you want to avoid that. So when taking these soils in cultivation, you want to be sure that the water table stays high and that you don't oxidize it to avoid this, and then these soils can be quite productive. Now, this is a picture of a soil where there has been oxidation, and then you see these yellow mottles, and that's called jarosite that forms when this oxidation occurs, and you can only reclaim these soils by excessive leaching and applying lime and all those kind of things, which is very expensive. So what was done here, and that was building on local experiences, and this was not invented, but the impact of science was very good, that you could add some quantitative measurements and data to what were already quite effective local practices, making ridges, adding up non-pyritic soil here, growing the plants there, having small ditches, and if the pyrite was deeper, you could make deeper ditches, and farmers could also grow fish in those canals, and the ridges could be a little bit higher. Very big differences in a small distance, and very local management practices had to be arranged, where science could give a good contribution to, I said it before, where the local expertise had already done some inventive things. They also made a map of the entire Mekong Delta. This was all done in cooperation with the Canton University, showing areas that were severely acid, moderately acid, and also the flooding was taken into account, and the areas were indicated where soil conditions were relatively favorable. And certainly in a communist country like Vietnam, such maps are very important because a lot of the planning processes go top-down and are really quite effective. We move to the Sahel, agriculture in the Sahel. Mohamedou Ganda, Joost Brouwer, Jan-Willem van Groenigen. You see here a picture of a local settlement, and what you see there around the boundary is that the vegetation is developed most strongly. Oops, does this work? No. Vegetation is developed most strongly next to the boundary. They put refuse over there and so on and so forth. You see also that the vegetation is developed around these trees, but you see other places where hardly anything grows. A tremendous spatial variability there, which is due to the very poor sandy soils that occur in these places. You see here a place where groundnut is growing. You see that there has been a tree before, and the fertility still plays a role, but there are other places where hardly anything grows. A very difficult situation. There's grazing, overgrazing in many areas, but the grazing has one interesting aspect that has been used by the farmers already for a long time, and that is corralling at night. So they collect the manure that the cattle produce during the night and spread it over the field. One of the specific results of this program was to show that the rates with which they spread the manure were too high, leading to erosion, leading to leaching when it was wet, in the wet period, and it could be reduced, those fertilization rates, with the same agronomic effects, making the use of the manure, the very scarce manure, much more efficient. These are soils in the dry period where you have enormous dust storms, and when you have showers, they're heavy showers. And the predictions of the IPCC are, the International Panel for Climate Change, that will be more severe in the future, probably. So this is rather difficult. But when it rains, the micro relief is also very important. So the water accumulates in the somewhat lower parts and not in the higher parts, and that has an effect very much on soil formation, more leaching here than there. And that also affects very much the natural soil fertility. And what you get now is that when you have experimental fields, according to the classic setup, this is one of the experimental stations, where every plot represents one particular treatment of fertilization application, you see you're in deep trouble, because this is not a homogeneous experiment here at all. So there's a lot of variation, and you can't invent enough statistics to deal with that. You really have to go out there and look at things and try to understand what's going on. The classical approach, as we use it, having fields and assume that they are homogeneous if you apply a certain fertilization rate, does not apply here at all. People have been very inventive. They have this system where they plant the sorghum in individual holes. So you can dose the fertilizer, the organic fertilizer, in there. They also have ridges to combat erosion. And this is an inventive system. It's extremely labor intensive, but labor is not in short supply, and this is one way of dealing with it. Whether it is a really sustainable approach for the future is, of course, another matter. We move to Kenya, the work of Erik Smaling and Jetse Stoorvogel. One of their major contributions, much more has been done, of course, is to point out, once again, that the balance of nutrients, when you look at many tropical countries, is very skewed. This is the N balance, the P balance, and the K balance, the potassium balance. You see here what goes in, different terms. You see there what goes out, different terms. And the out is quite a bit bigger than the in. This is a structural problem. It's not really solved at a given point for reasons that are not quite clear. The fertilizer subsidies were stopped. It was not a very good idea, and this is one of the major concerns when dealing with these countries. And one thing that was obvious in that study, but also in other studies in Africa, was that different soils have quite different potentials. Let me just mention three of them. We have what we call a feral soil in Kenya in this case. It's a highly leached tropical soil with a high iron and aluminum content. A high iron content leads to the red color. They have a low fertility. They have very strong fixation of phosphates by the iron, but they have a very good and very stable soil structure. When we go to Nitte soils, a picture from Uganda, they're relatively fertile. They have relatively little P fixation. They have a high cation exchange capacity that is effective, and they have a relatively good structure. When we go to alpha salts, also found in Kenya, you have soils where the clay has been leached from the surface and accumulated in the subsoil. That makes the surface soil much less stable, so they're much more prone to erosion. So they have an unstable surface soil structure, low fertility, and relatively little P fixation. So there's a lot of difference there. And that's important to realize. You see some agronomic experiments where they just take a fertility sample from the surface soil and use that to plan the land use. You have to take into account these profile characteristics because they play a very important role in the dynamics. And soil is a dynamic living system where you have to look at the whole thing and not only at a little part of it. This is all courtesy from Isrik in Wageningen, a picture from Brazil that also indicates that the soil classification, these three names I mentioned, are worldwide classifications. So what applies in Africa also applies in South America. And in this map, in this map, those three soil types are indicated in various patterns as they occur in the landscape, and again, they have a major effect on the land use. We move to Costa Rica. Huizing, Stoorvogel, Jeroen Huizing, Jetse Stoorvogel, Alfred Stein, Egbert Spaans, Lambert Kooistra, and Ton Veldkamp. This is a picture where the original tropical forest has been cut. Happens in many areas. You have a secondary forest and there is extensive grazing. This is a typical, very typical picture for those kind of situations. Extensive work was done in the Atlantic zone of Costa Rica, where much agriculture occurs. This map shows the amount of soil degradation that is occurring there. So, compaction in terms of compaction, nutrient depletion, and contamination. And having this overview based on a soil map can help you to focus remediation measures. Sometimes also because there's an active environmental program in Costa Rica that was very valuable in that particular context. Also a map, and I just showed two maps, there were many more, where the potential production areas for agricultural production was indicated, also excluding, involving major differences depending very much on the soil conditions. Jetse Stoorvogel developed a decision support system for banana fincas. One of the results was that 70% of yield differences within banana fincas could be explained by soil differences. He had a PICO yesterday where he showed that he's continuing this type of work and finds that fertilizing these soils is not only good for having more growth of the banana, but also for combating pests and diseases. And there's still quite a bit of work going on, and the banana crop is an extremely important crop economically for many countries, certainly not alone for Costa Rica. Now, we have here a picture of a natural surface soil in the natural forests, natural forest. What we see is that when the natural forest is cut, then with heavy machines you get severe compaction of the soil. This is the loose surface soil, and when you get compaction, you get compacted aggregates with cracked in between. What we found was that there is a major differences between different soils in terms of their resilience. If you had relatively young soils, endosoils as we call them, they came back very quickly after compaction because the biological activity was very high. When you have older soils, it took much longer. It was much more difficult. You know, soils are like people. If you have a young person and you give him a kick, he or she bounces back right away. If you have an old person like me, you kick it, well, he bounces back, but it takes a little bit longer, right? Now, I dare ask the question, how would Alexander look at all of this? He's not here, so it's an easy question. I submit to you that simulation models of the soil, water, plant, atmosphere, ecosystem as applied in the regional Philippine, Kenyan, and Costa Rica studies are ideal to realize the interdisciplinary vision of Alexander. Because you have to work together, so scientists, hydrologists, agronomists, economists, and all that. The studies in Vietnam and Sahel showed the complexity of the soil plant system, requiring detailed on-site measurements and custom-made solutions, building, very important, but building on, but significantly refining local expertise. A lot has been done already by farmers all over the world and certainly in developing countries. And it is very important to listen very carefully to all these things and build on from there. And we have a contribution to make, but not out of the blue. That was very clear from these studies. And on-site measurements were crucial for every study. And geostatistics particularly was applied to quantify spatial patterns, like in the Sahel. How to go about it? Well, you can deal with that with geostatistics and can make sense out of it and optimize your sampling schemes, for example. A clear example. So overall, we feel, I guess it's relatively easy to say that we were working in line with Alexander's spirit, and we did not realize that, of course, at the time. Now, looking at the future for developing countries, and very, very broad brush, don't get me wrong here. We know the numbers. The world population will increase to 10 billion people by 2050. Climate change is likely to have dramatic negative effects on agricultural production. Water shortages will increase. Land degradation is serious and is getting worse. Markets don't work. Armed conflicts cause serious suffering. Economic growth hardly benefits ordinary citizens. Birth rates remain high, etc., etc. Stop the world, I want to get off. But we can't, of course, and nor should we. But there are also many positive signs, and I like to focus on that. First of all, just rather arbitrary, the Great Green Wall. Local initiatives in the Sahelian countries of doing agroforestry, planting trees, planting shrubs, and all that. Images from Google show that this has really had a very clear and dramatic effect. Now, of course, the current drought in the east is a severe setback, okay, but overall, it's a very positive sign. We have the introduction of mobile phones. Already 1 billion mobile phones in Africa alone. It's a real revolution, allowing farmers to contact with markets, also allowing interaction with educational programs, so on and so forth. We had this cover in The Economist, the planet of the phones, not the planet of the apes, but the planet of the phones, right? By 2020, 80% of adults will have a supercomputer in their pocket. That's an enormous prospect, if it is used right, of course. Now, this is the well-known picture from NASA, and Africa is the dark continent, parts of Asia are, parts of South America are. But there is a tremendous development in terms of introduction of solar panels. When you look at the average annual sum of global irradiation, when you look here in Africa, also in places here, you're at about 2,400 kilowatt hours per square meter, and we here in the north sit around half at 1,200, right? So that's an enormous potential, and with the price of solar panels going down significantly, thanks to maybe the Chinese a little bit here, we have more and more introduction of solar energy to help with the energy need. So with the phones, we had leapfrogging. They did not have the solid lines. With the solar power, the energy, we will have leapfrogging as well. A few years ago, there was the number of 600,000 homes already that were served by electricity derived from solar power. In the soil field, we have the development of sensors, new sensors that can sense nutrient content in soil, organic matter contents in soil. It still needs a bit of work, but it's a dramatic improvement compared with the classical procedure where you had to take samples, go to the laboratory, wait for a while and get it back. A very effective procedure, by the way, but we can now, with modern methods, do this a lot better. And this is also a development that is, I think, quite promising. We see that agricultural production is increasing. It is slow, it could be faster, but it is increasing. You see the lines go up just a little bit here, quite a little bit here. That's a positive sign. There is the whole issue, of course, of land grabbing. That's a serious issue. Land is interesting for investment because it is solid, it is there, it will stay there. And on the stock markets, all these bubbles, you don't never know what the bubbles are going to do, right? And we see this all over the world. It's not only in developing countries. And it has a bad name because people have come in, bought land and made all kinds of promises about jobs and benefits and all that have not materialized. That's very bad and it's unacceptable. But I understand there is thought now of making new rules and guidelines that will allow this a little bit. And then it is a good development because larger areas, if they are used with modern agricultural techniques, it can produce more food for all these people, because to do that with only on all these little plots of 1 to 2 hectare, these very little farms, is going to be very difficult for Africa to get food security in the future. And what I also want to point out in this picture is that land grabbing, so buying land by third parties who don't directly farm the land, is not only a problem of Africa. It has happened in Indonesia, in the Philippines, in Vietnam, in Ukraine, as a matter of fact, in Brazil and everywhere. So it's a thing that will not go away. So we better make sure we get good rules so that the people concerned benefit, get jobs, get more prosperity, and that contributions are made to agricultural production. There are many developments of soil conservation that improve soil-degraded lands. There is this one report, Desire. There are many others. The BOCAT program is also quite effective. Very good examples. This is a picture, arbitrary picture from South Africa, where they, on a slope, they build stone walls. They have cover crops, the rest of the crops on the surface to protect it. Very effective measures. The well-known pictures from China, the Lush Plateau, where terraces are being made, and All the status of the world soils has been summarized in a very nice report by the International Technical Panel of Soils in cooperation with FAO, a book that came out in 2015, but they conclude that there are still very serious problems with land degradation. We know many methods to overcome those problems, but there are difficulties sometimes in getting them adopted by the people concerned. That is quite a concern. There's another element that I would like to stress very much, because I think it's the major issue facing the science community all over the world at this point in time. And I'm not the only one to say that. Again, a cover of The Economist, Post-Truth Politics in the Age of Social Media. Relations between science and society are changing. We have to get used to post-truths and fact-free attitudes and alternative facts. Now, how we handle this, we're not really good at that. Now, we can realize that Alexander of Humboldt was already quite aware of the underlying causes of these problems. I find it quite remarkable to read that he, in dialogue with poets like Goethe, he was quite aware that facts are experienced differently by different people as it involves different emotions and values. And it's very much associated with culture. He warned against developments where science may feed the brain while ignoring imagination in the process. That is a very valuable message for the 21st century science community, I would think, right? And let's face it, the truths and facts are the lifeblood of science and research. So this hits home, doesn't it? How to react. And of course, science does not just offer just another opinion. But the absolute truth does not exist. The scientific method tests hypotheses and produces reproducible facts based on validated methodologies and statistical analysis, next to even falsify, right? That's what we say. Huh? To some, we are the remote elite. That's what they think, right? And how does the public interpret that? When we say, well, science is never sure, they say, no, those people don't know what the hell's going on, right? That's the reaction that you get. So the only conclusion I can draw is that we need a storyline in front of the curtain, and we need a storyline at the back of the curtain, so to speak. Just an example. The French have proposed what they call the 4 per mille proposal. And that means that a proposal to increase the organic matter content of soils as a very important mitigation process for climate change. Soils can absorb quite a bit of carbon. That was proposed at the climate conference 2015 by the French foreign minister. Fantastic. I went to a conference on soil security in Paris, and the agriculture minister was there, also explaining this proposal. And he talked, without a piece of paper that one of his assistants had written, he talked about this in a very knowledgeable way. Fantastic. Now, soil scientists will say, yeah, but can we do this? What are the bulk densities of these soils? What kind of methods have been used? What is the very valid, but do that behind the curtain. Okay? And in front of the curtain you say, fantastic, we are very happy that the minister is saying this kind of thing, vive la France, right? There's a little bit more about the meaning of truth and facts. Post-truth does not exist either, because a single absolute truth does not exist. I said that before. There is no absolute true form of land use or land management. There are a lot of conflicting interests, and you come up with a compromise that everybody is unhappy about, but because nobody got what he or she wanted. That's the reality. And it works. It's no problem. Environmental problems are wicked by nature. No single magic solution, always a compromise between conflicting interests. Okay, we can handle that, but we have to be aware of that. We are often in a frame of mind that there is a problem, we investigate it, and there is a solution. We have measurements and that's it, and we move on to the next one. Well, that's not the whole story anymore. So you have to look at it in a much broader conflict. And there are many conflicting truths corresponding with different visions. Let's only look at biological agriculture versus high-tech agriculture. There are different visions on that. That's quite legitimate, but they experience different truths. That's not something to combat. It is something to accept and work from. And each vision is supported by their own facts. They're often framed facts, because they have to fit in that perception of the truth. And facts that don't fit are omitted. And if you can't use any facts at all, you make alternative facts, right? That's also a possibility. And if we are really honest, I think, when we say post-truth, what we really say is post-our truth. There's a touch of arrogance there, right? And there is no such thing as fact-free politics. There are political facts, but only framed facts that fit in a particular political discourse. The rest that do not fit are ignored or vehemently denied. And if this doesn't work, alternative facts are produced, as I said a moment ago. Now, our Pavlov reaction when people don't accept what we say is to explain it again. And say, yeah, you don't understand. And we make new measurements and whatever we do. Don't do that. It doesn't work. We have to get used to post-truth and fact-free and see how we handle that. But I think alternative facts are really a bridge too far. Now, I think I had this before, right? Alexander von Humboldt was already aware of all this. Yeah, I had this before, right? Yeah? I put it in twice, so I don't do it again. I think it fits here too, though, and I think it's worth repeating. He saw that facts are experienced differently by different people, as it involves emotions and values and culture, I should add. He warned against developments where science may feed the brain with abstract data while ignoring imagination in the process. Good advice for the modern arena, as I said before. Besides, I think we have to say that the internal organization of the scientific community, our scientific community, squeaks a bit. Weary scientists suffer from performance criteria too much focused on publications and funding generation. There is often no time to really interact with stakeholders because that takes a lot of time if you want to do it honestly. Exploding numbers of scientific journals, not enough reviewers. As government funding decreases, often less than 10% success rates of government research programs need for external funding, and how do we maintain independence? All I'm saying is, when you put this all together, I don't think it's a very good example for developing countries to follow. So my thing would be, before I do that, though, I think we should also give credit to the fact that the scientific community is reacting to this. There is in the Netherlands a new standard evaluation protocol for research since 2015 that says publications, yes, sure, that's needed. Less emphasis than in the past, but societal relevance is as important. And viability. Societal relevance is not defined, though. So I think it's our task to redefine that in such a way that it becomes a good, viable goal rather than another set of criteria that we have to check on forms that we have to fill in, okay? So there is a movement, and that's a very good movement. But I would say soil scientists in developing countries, and maybe I can extend it to environmental scientists, they would be well advised to learn from experience elsewhere and leapfrog in their own way to an innovative and vital scientific environment. They leapfrog with the phones, they leapfrog with solar electricity, also leapfrog with the science. And I would make some suggestions with a focus on soil and environmental science, particularly on soils. And it's not meant to be a blueprint, by no means, because this is complicated. But I'd like to share some ideas that can be the basis, I hope, for continuing discussion, because we should discuss this. We cannot put this under the table, right? We should discuss it. Okay, quickly. Define clear goals in what you do. That seems obvious, right? Well, I read quite a few papers, and I wonder that in which the question that is being investigated is not clearly articulated, and sometimes it's very hard to find. So we need clear goals, and I think it's very attractive to take the 17 United Nations Sustainable Development Goals as the overall goal for everything we do. And every project you do, ask yourself, what kind of United Nations Sustainable Development Goals are relevant here? And it usually fits because they're very broad, right? And we can ask, as a soil science profession, what can we offer? I'm not going to go through all these numbers. There are 5 where soil plays an important role. It has to do with food, it has to do with health, water, climate, and ecosystems. There is this picture that has been used several times this week. It's in a paper by Kirsten et al. 2016. What this illustrates is that soil science is here. We have the soil functions as they are defined by the European Union, and we have the Sustainable Development Goals. But what we say is, okay, folks, in soil science, you cannot do it alone. You need to interact with all these other disciplines and focus on ecosystem services, okay? And then move on to the Sustainable Development Goals. So interdisciplinarity is crucial, and again, the modeling effort, I think, is very helpful in kind of doing that. That's basically what this diagram shows. Now, there is another reason to define goals. Expanding databases, new models, and a continuous flow of remote sensing and monitoring data can become suffocating, isn't it? Pfft. Lots of trees. Where's the forest? Are you familiar with this tale of the sorcerer's apprentice? I suppose you are. The apprentice was learning from the sorcerer, and he learned a formula for brooms to carry buckets of water. Rather funny, but anyway, that's the way the fairy tale goes, right? So he used that formula, and then the sorcerer went away to do shopping or whatever, and then the broom started carrying water. But the guy did not know how to stop. He did not know the magic formula to stop the brooms from carrying water. So the water came up and up and up, and he almost disappeared, right? And then the sorcerer came back and gave him the formula. I think sometimes our modern scientists are a little bit like the apprentice of the sorcerer, right? Overwhelming, and somehow we have to find a way in there, and our goals can be extremely helpful in that particular regard. Because without goals, where do you go? 2, adhere strictly to scientific principles. That seems a bit of an open door too, right? But still, it's important. Scientific research presents not just another opinion. If people say that, that's nonsense. We have to really show that it is nonsense. Define the problem, formulate a hypothesis, choose reliable methods and procedures, or develop new ones. Make adequate number of measurements and observations to allow statistical expression of results, and pay attention to the way results are communicated. Lousy research is the best way to lose your reputation. Be aware of that. Engage stakeholders by applying knowledge as a tool and stay in charge. I like this little diagram. I've showed it earlier this week. It's originally from Cornell University. It very simply defines knowledge in terms of 2 axes: qualitative, quantitative versus empirical mechanistic. K1 is stakeholder knowledge, empirical, qualitative. K2, you get more into the expert area. There's better understanding of the underlying mechanisms. Here you get into the research arena. It can be empirical, but quantitative. Think of regression analysis, for example. K4 is existing methods and models and things like that, more mechanistic. And K5 is quantitative mechanism. It's the kind of stuff, when you do that, you have the biggest chance that you are accepted in international scientific journals. And don't get me wrong, this is very important that we do this. But if you take this approach from K1 to K5, when you work on a certain program, it has a number of great advantages that you don't just jump in with K5, which we sometimes do. Right? There's a problem. Okay, I have a model, I have this, and develop something new. Do it, that's it, result. That's K5 sec. No, I say do it this way. Because it means if you do this, you take these stakeholders along in a learning experience, a joint learning experience, by all means. We have to learn something too. You create ownership. It's not their problem and our solution. It's our joint problem and our joint solution. Very important. And I have the feeling that one of the major reasons for this fact-free business is that people feel they are not being taken seriously. They're being talked down to. We tell you how it is. They all have internet. They look up Google and everything else. I'm not talking about the 10% of people that are against anything anyway. You know? I'm talking about the silent majority. It's a loaded word, I know, but who is disappointed. They want answers, they have real questions. And take them along on the journey, that's a good thing. There's a second element in this diagram that you may find at some point in time, that K3 solution solves the goal. The problem solves the goal that you're striving for. So stop. You don't need every time the cutting edge stuff to solve your problem. And that's very important also for the political arena. We have a Pavlov reaction to the I was a member of the Scientific Council for Government Policy in the Netherlands, and the most common question I got from politicians was, you guys have been at it for 100 years. Do you never know enough? Well, you know, no, of course, but sometimes we can do this. And to show when you make a request that we have a problem, when we go until this point, it's not enough, we need more, or this, we need more, then that is a much better way to explain your desires for money and for new research than to just ask for the money because I'm a researcher and I'm important and all that kind of stuff, right? So it's important to do this. These are two major things that I think have to be taken into account. And I compare it a little bit with driving a car. You will never start in fifth gear, right? Some people do, but it's not very successful. So start with this and then move along. That is a good way of engaging the stakeholders. And of course, an automatic transmission never goes together with scientific research, right? And why climb the mountain? Well, there is sometimes an argument about basic research, fundamental research, that why climb the mountain? Well, because the mountain is there. Oops, because the mountain is there, right? Well, that may be true for theoretical physics and astronomy and genetic research. I think for land-related research and soil and environment, I think the story should be, we climb the mountain, we want money to do that because we are pretty sure that on the other side of the mountain there are data to be found that are essential for us to solve our problems. Okay, you need the story to go with it. And that basic research is crucial. If basic research stops, then that's the death of science. So, but we may have to spend a little bit more time in arguing why it is needed in a particular context. And remember, the scientific principles not only apply to K5 research, but to K2, K3, and K4 as well. And there was a very interesting PICO yesterday on urban gully erosion and the SDGs. A case study from Uganda by Guido Zoleggi and Marco Bezzi. I don't know whether they're here, but that was a nice study where they used K3 research. They had a village with a lot of problems, but they helped them by using their expertise, but adding to it, making some simple calculations, not very complicated, no big models, no big monitoring campaigns or whatever, and they could make a very effective, they could do a very effective thing. That to me is science that is top of the bill as well as a very sophisticated stuff. That, again, is very much needed. Now, we talked about the knowledge, but you have to apply the knowledge as well. And I like very much the DPSIR system from the European Union, distinguishing drivers, pressures, impact responses, and the state of the land. These are the processes. You have the state of the land in the past, then you have drivers and pressures, they have an impact, they get a response, you get the state in the present, and then you have the future. Different scenarios where we have a response as a consequence of drivers and pressures that have an impact. What is very important here is that anything can be done anywhere. Never say that something cannot be done. Anything can be done anywhere. The only thing is that what we can do is if you do that, these are the economic, these are the social, and these are the environmental consequences. And you guys choose, the stakeholders and the policymakers. Sometimes scientists are manipulated in a position that they choose, and they're being said, yeah, you told us the wrong things. No, no. We only show options because every scenario is one of these truths we've been talking about. Everybody has, there are different truths, there's not a single one. And we show the consequences. Options, one has to be selected. And the nice thing is that you start out with their own truths and their own scenarios, but as you work together with the stakeholders and the policymakers, you also develop new scenarios, joint scenarios based on common learning that really take people along. And again, it takes time, but I've seen examples where that works very well. But also run their own scenarios. Don't only develop a joint scenario and only run that. No, also show all the other ones on the basis of everything can be done anywhere. That is important to do that. Then the fourth point for soil science is avoid atomization of soil science and associate with physical geographers. Start with pedology. I think it's a bit isolated. You have pedology, physics, chemistry, biology. Start with pedology, soils in the landscape context, add the water, then the chemistry, and then the biology in that sequence. We see sometimes people in biology where you have no idea what the soil is, what the water regime is, what the chemical characteristics are, and so on and so forth. And that is not good if you want to communicate with other professions. Soil is a living system in the landscape context, and that's what you should project. The fifth point, almost the last point, is develop storylines to facilitate communication. See soil functions as part of production or ecological change. Tell the whole story from problem definition. How did it work? Who was involved? What did they want to do? What did we decide? How did we talk? What did we consider? What were the results and are the results implemented? The whole story, right? And now what we often have are unconnected bits and pieces of research that don't do justice to what is often accomplished by research, because a lot of that is accomplished in my view, and always connect with the SDGs, as I've said before. And the last one is preserve intellectual vigor. Don't restrict and burden scientists with too many bureaucratic performance indicators and judge output on the basis of quality, not numbers. And I'm repeating what has been said in other places now, also in administrative places, so we are going the wrong way, I think, but this is still very much a point. Create longer duration programs that allow time for reflection and effective communication with stakeholders and policymakers. Having no time now is self-inflicted, because these are our problems. We cannot say it's the politics and it's the stakeholders that don't understand us. No, these are our procedures, and it's up to us to change it. We can. The movements are starting, but I think they need to be strengthened. I heard very interesting talks this week about modernizing education programs, installing this kind of attitude with the students. There are many initiatives going on that I think are extremely valuable, because you have to build this up from the bottom. So, in conclusion, it's great to be a soil scientist and to be able to substantially contribute to realizing the Sustainable Development Goals. Let's be inspired by the inquisitive and open mind of Alexander von Humboldt as we proceed. And the scientists in developing countries are encouraged to develop their own ways aimed at unleashing the fabulous and fascinating powers of science. And don't be discouraged by fences. Avoid overkill. Sometimes making holes in fences may be more effective than trying to remove them. Remember that one. So, what does it boil down to? Genuine engagement based on well-deserved pride in what we have to offer. And I'd like to acknowledge the contributions of many people. I will not read it all now. I will write a paper. I hope it will be accepted, and then you can read it. Thanks to our PhD students, our co-promoters, and also contributions from the Eco-Regional Methodology Fund that I could not discuss here because of time limitations. So that's it. Thank you very much.
I think the whole audience are thanking Johan Bouma also for this very inspiring lecture, presenting the problems that society is facing, giving us a good bite of natural science philosophy related to the soil sciences at the basic level where we all can follow it. That was really great. Thank you. There's time for questions or comments. Oh boy. Well, no one can speak as fast as you, Johan, but no questions or comments? Well, then I think we will just thank Johan once again for this fascinating lecture, and I hope that it gave a lot of, well, I'm sure it gave a lot of inspiration to several people in the audience. So thank you very much, Johan. Oh yeah, let me just remind you that the lecture was actually streamed. So it means that the lecture will be available at the EDU website, so that you can recommend colleagues to visit the website and follow the lecture, and you can go back and revisit the lecture. Thank you.